What I'm about to talk about will be a major spoiler for 4D Golf, so you really should play the game first before watching this. But with that disclaimer out of the way, how did I do that finale? Yes, it is actually a 5D game, and that was a significant part of the development time, maybe even a third of it. And if you thought any of my other devlogs were complicated, oh boy, where do I even start? Since I already built a 4D engine, could it be as simple as just replacing some 4s with 5s? Well, there's actually a few places where that is reasonable to do, like with the colliders, physics, camera controls, and other utilities. But even for those, it's not so simple. You see, since the code is written in C#, there's no way to do proper templates with numbers like I'm used to doing in C++. But I've never let things like language specification stop me before. So I literally wrote my own preprocessor to add integer templates to C#. Yes, this was necessary.
Microsoft!
But a preprocessor can only take you so far. Most things are a lot more complicated than just replacing one number with another. For instance, Unity only supports up to vector 4 and matrix 4, so I had to remake the basic classes myself for things like vector 5 and matrix 5. And then there's the 5D slicing. How can I even render 5D stuff to the screen? Well, I discussed how I made the 4D meshes in Devlog 3, and those techniques do generalize to higher dimensions. It's just that 5D is way more complicated and impossible to visualize. In that last devlog, when we sliced a 4D tetrahedron with a 3D space or hyperplane, we cut the 1D edges to get up to 4 intersections, which can render as 2 triangles. But what I'm showing here isn't strictly correct, because this is a 3D tetrahedron with a 2D plane slicing it. It just happens to visually match what's going on in 4D. But there's not really a similar way to show that for 5D. When you slice a 5D pentachoron with a 3D space or hyperplane, we intersect 2D faces to produce up to 5 intersections, which can render as 3 triangles. Yes, a 3D space intersects a 2D plane in a single point in 5D. It's really hard to wrap your head around. Even weirder is how you determine which faces are intersected. In 4D, you just look at which side of the hyperplane each vertex is on to find out if the edge will be sliced. So there's 2 to the 4th or 16 possibilities to consider in the lookup table. But in 5D, it's harder to explain, but you have to compute a directed edge graph kind of thing, and if the triangle has a cycle, that means it has an intersection. I don't really understand it, but that's just how it works out. Since there's 10 edges, that means this time we have 2 to the 10th possibilities, or 1024 combinations. Adding all those bits plus the index bits results in a much larger lookup table, which is now a 128 by 64 RGB texture. And here's how that looks. Generating and using this lookup table was definitely the most challenging part of getting 5D to work. And it's the core reason this game is able to run at all with reasonable frame rates. Now, the 5D struggles don't end there, of course. First of all, GPUs were not designed for 4D rendering, but they're even more not designed for 5D rendering. 5D vectors and matrices are just not supported at all, period. No data structures, no dot products, nothing. So how did I get them working? Well, I just used more fields. A 5D vector is really just a 4D vector and an extra float. And a 5x5 matrix is really just a 4x4 matrix with an extra 4-row, 4-column, and single float. I was able to make that somewhat tolerable by creating some shader macros, but it's still very annoying. You know what's even more annoying? Remember in Devlog 3 how I had to store an entire copy of the tetrahedron for each 4D vertex? Well, now I have to store an entire 5D copy of the pentachoron at each vertex. That's a lot of data to transfer. Luckily, I can finagle the fields a bit to group them together for a slightly more efficient GPU transfer. And don't get me started on the vertex normals. To reduce the size of this massive vertex data, I compress the normals to 8 bits per coordinate. Then unpack it and interpolate them in the vertex shader, which makes for some really ugly and confusing code. But sometimes that's just the way it has to be. Anyway, those were the most challenging parts of the shader. The rest of it is more or less the same as 4D, but with an extra dimension. In fact, I designed the shaders to generalize by making the dimension a parameter in the shader preprocessor. So one shader can be used in both dimensions. The only thing I have to define for a custom shader is the 4D and 5D fragment color, and that's polymorphism at its finest. That still leaves the question, what about the 5D meshes? How do they even work? Well, it is mostly similar to the 4D tetrahedral meshes, except with 5D pentachorons instead. But generating 5D meshes usually means I need to start with a 4D model and do an operation on it, like an extrusion or revolution. So there's an extra step on this modeling ladder to do anything in 5D, which is only possible because I can use all the 4D stuff I've already made. The main problem with 5D meshes is that they're enormous. Let me give you an example. If you wanted to make a flat square in 3D, you only need 2 triangles. When you move to 4D, it's actually 3D things that appear flat, and a flat cube ends up needing 5 tetrahedrons. So how many pentachorons does it take to make a flat tesseract in 5D? It turns out 16 of them. There's an exponential growth that happens when you add a dimension. So 5D meshes are typically 10 times larger than 4D meshes for the same visual shape, which are themselves about 10 times larger than a similar 3D shape. That meant I had to really limit what kinds of objects I could make for the Beyond courses, and rely more on the procedural shaders to fill in the details. Believe it or not, the worst culprit of inflated triangle counts was the ball. It turns out there are no good ball shapes in 5D because it doesn't have any other point group symmetries, just the cube and tetrahedron ones. All the other dimensions around it have more symmetries. Why is 5D so cursed? I don't know, but it made it a real pain in the genus to make a golf ball that wasn't ridiculously high poly. You'd think the ball would be the easiest shape to make. So I ended up using the pentachoric triscylla octacosa. Let's just call it the 3840 Terra, since that's how many terons it has. Here you can really see that exponential growth as the dimension increases. It's an awful bang for your buck, but there's not much I can do for hardware that wasn't designed for this in the first place. Building the tracks was also extremely obnoxious because these have to be built vertex by vertex with a manually crafted algorithm, just like in 4D, but twice as bad. I ended up with ungodly functions like this, with 35 arguments and a full screen of conditionals. Thankfully, these scripts just generate the track assets, so that code never actually runs in the game. I hope that forgives my coding sins. The way these 5D track pieces connect is also surprising. When connecting two flat pieces in a 3D environment, there's 2 possible ways to connect them. And in 4 dimensions, there's 4 possible ways. So in 5D, there's maybe 6 or 8? Nope, there's actually 24 different ways. Since the boundary of a 5D track is a 3D cube, it's the same as asking how many ways can you connect one cube to another. There's 6 faces times 4 orientations each, which is how you end up with 24. All in all, designing the courses for the Beyond levels wasn't really that difficult. It's exactly the same track building system I used in 4D. The hardest part is trying to create unique mechanics that work in 5D but not in 4D, so players have to think 5-dimensionally. For example, this double rotating platform that you can walk on. I needed to make sure there weren't any levels that just became 4D when you looked at them from a particular angle. So that's a peek under the hood of what a 5D game is really like. I'm so happy to finally get this off my chest. It was so hard to keep this part secret, especially with all the jokes in the comments. But I'm glad people enjoyed the reveal and gave such a positive reception to the game. So keep spreading the word and let your favorite streamers know about the game. It's been cool to see everyone not just play 4D golf, but really start understanding 4 dimensions on a deep level. It's an intuition you only get from hands-on problem solving, just like today's sponsor, Brilliant. Hands-on interactive learning is a way more effective way to learn a difficult subject, from math and data analytics to programming and AI. Brilliant has thousands of courses for anything you're curious about and gives you personalized lessons to build your critical thinking skills. They even have a great course on vectors, which are the building blocks for working in higher dimensional spaces. So if any of this video went over your head, this could be a good place to start. You can try everything Brilliant has to offer for a full 30 days free, so visit brilliant.org/codeparade or click on the link in the description. You'll also get 20% off the annual premium subscription and support my channel. So thanks again to Brilliant for sponsoring this video. VR and online multiplayer are still coming soon, as well as the source code for the engine. But I'm also looking forward to taking a break from the devlogs to make some classic Code Parade videos. And besides purchasing my games, you can always support my projects through Patreon, Ko-fi, and my merch store. It's been an amazing journey, so thanks for watching.